Hello everybody, welcome to my second C++ tutorial. This time we're going to go through a few things. First of all, we'll look at comments, and then we'll finish up looking at variables. Okay, so basically comments in C++ are messages from the programmer to the programmer. They're completely ignored by the C++ compiler, and they're only used to clarify exactly what the code is doing in your language. Visual Studio 2010 colors comments green. And there's two styles of comments in C++. There's a single line comment which starts with a // just like this, and that's anything to the right of the // will be ignored by the compiler. But there's also block or multi-line comments where everything between the /* and the / is also a comment, so we can comment out big blocks of code or write paragraphs to ourselves in comments. Here's just a little example of some code with comments. So you can put these single line comments after a statement. We see here return 100 and then a semicolon, and after that we've got the comment. This would be up here an example of a multi-line comment. Okay, so comments are also useful for blocking out code that you don't want to run temporarily. Maybe you think a particular couple of lines of code might be causing you a bug or something. So you can comment out that line of code and run your program and see if it's causing the bug. But some programmers believe this usage of comments is bad form. So be careful. There's lots and lots of rules and regulations about how and when to comment, but there's no real standard. In the end, the right way to comment is whatever the team decides. So if you're programming in a team, everybody comments the same, you get by okay. Use comments really often. There's really no other way to say this. Commenting is your friend, and programming source code doesn't make nearly as much sense to you as your native tongue. You probably noticed already. Explain absolutely everything in comments that's not blatantly obvious, and sometimes even explain what is blatantly obvious. Commenting practices can make or break a programmer, and they aren't even read by the compiler. Comments are extremely important, folks. Anyway, you'll develop your own style for commenting. So on to variables. This is a really, really important concept in programming. A variable is basically a little box stored in RAM, which is the computer's memory. RAM is short for random access memory. And that comes about from, as opposed to tapes, they used to use tapes in the 70s. And tapes couldn't access just any old box in the memory on a tape. You had to access sequential boxes, or you'd have to rewind or fast forward the tape. So tape systems weren't random access, but the ones that we use now, the RAM sticks in your computer, are random access. We can pretty much access any byte that we want. We'll go through what a byte is in just a second. Anyway, each box or each variable has a name and a value, and we can change the value of a variable using mathematical expressions, and we can display the values using cout, which we'll do at the end of the tut in a little example. C++ allows the creation of custom data types, but all data types are created from the fundamental data types. Okay, so here's just a little illustration of RAM. It's pretty stylized, but this is basically what it looks like. So the dots here, or the dots here, and over here on the right, that just indicates that RAM really goes on for a very long time. If you've got 4 gigabytes of RAM, then this is going to be 4 billion odd little boxes that you could store. This first box over here is the lowest in RAM. This is the first one in RAM that I've drawn. There's more boxes over here to the left and more boxes over here to the right, but this is the first one that I've drawn and named. So this variable just here is called I, and it has the value 65. The next one beside that is called counter, and it has the value of 1546. Then we've got T, which has the value 45. Another box called my big var, which has the value 0. And finally on the end I've drawn another one which has the value A, and I've called that S. So these 5 just here are variables in RAM. Just little boxes with values and names. Note that the boxes aren't the same size, so variables aren't necessarily the same size. Some of them are big, some of them are small. Oh, here we go. Yeah. Alright, yeah, we just said that, yeah. Yeah, basically the larger a variable, so counter here is about twice the size of t, just here. See the t variable, the t box, is about half the size of counter. So counter could potentially hold a larger number than t in this little diagram. And my big var just here, it has 0 at the moment, but it could potentially hold even larger numbers than counter. Okay. We'll go through exactly the limits of the variables in a minute, but first we should look at some terms. So an integer, this is will come up time and time again in our programming. Integers are whole numbers, so 12, 189 or negative 29,093 are all integers. They're whole numbers, they don't have a decimal point, they're called integers. And this is usually abbreviated to int, int. And in mathematics the integers go on forever. So the integers are actually the set of all whole numbers. Negative, 0, and positive, all the way up to positive infinity. But in computing, the integers have a limit, which we'll look at in just a minute. The next term is floating point. Now, floating point numbers are numbers with a decimal point. So 45.6, negative 9.29, 71.0, and 6.3f are all floating point numbers. I've put the f here to indicate that it's actually a smaller floating point number. We'll look at this in just a minute. But the 6.3f just here will occupy less space in RAM than the 71.0, which hasn't got the f. We'll see why in a second. Signed is another term. Sometimes we need our integers to be capable of expressing both negative and positive numbers, and these integers are called signed. So if you've got a whole number, and maybe it's got to be negative, or maybe it's got to be positive, then you'll want to store it in a signed integer. Unsigned, on the other hand, can never be negative. They range from 0 all the way up to some positive number, and they can't be negative. So if you've got an integer and you know that it doesn't, it'll never logically be negative, you can use unsigned integer to store that, an unsigned variable. There's no sign bit. Signed and signed and unsigned apply only to integers. All floating point values are signed. Yeah, that's true. All floating point values are signed automatically, whereas integers we get to choose whether they're signed or unsigned. Okay, some more terms. A bit, a single bit, bit, bit. This is the smallest thing in a computer. It's either a 0 or 1, and that's it. It can only be a 0 or 1, short for binary digit. The computer is nothing but a collection of trillions of them all acting together. Yes, it's rather a large sum of them, but the computer is nothing but zeros and ones. You might have heard. Computers count in binary. Okay, so the byte is another term. This is a collection of 8 bits all acting as a single unit. The byte is the smallest practical thing in a computer, so a computer can't actually access a single bit easily. Usually it works on bytes, but the byte is made up of 8 little bits altogether. So a byte, what's this? Bytes are a number, and we can write them in binary as bits. We write binary numbers the same as decimal. Yeah, we're not going to go into binary just at the moment, but this might be what a byte looks like. So we usually write 8 bits out, and the lowest bit, or the ones column, just as in base 10 or decimal, the way that we count. This is the first digit, so that actually means a 1 just there. And this 1 just here in the what's that, third box, or bit number 2, would indicate 4. Alright, that's good. Yeah, anyway, a byte is 8 bits. So here are the fundamental data types. I've basically just listed them all out here, and I've coloured the ones in red that I think you tend to use most when programming in C++. And with each new compiler, the sizes in bytes, and therefore the range of the fundamental data types can change. Yeah, it changes over time. So an int just here is 4 bytes at the moment, whereas back in the DOS days, back in the 16-bit CPU days, an int was only 2 bytes long. And some data types have other names. So signed int is exactly the same as int, or in other words, just int by itself means a signed int to C++ compiler. And signed char is the same as char. Alright, that's good. So basically we've got a char, which is 1 byte long, or 8 bits, and that's used to hold a single character, e.g. A or 6. You put chars or characters in single quotes, just like this, A or 6. That can also hold things like grammatical, what would you call it? It's not grammatical, it's punctuation marks. Yeah, so say a full stop or a question mark, any single character on the keyboard pretty much. There's also unsigned char, which is also 1 byte, and this is a positive integer because it's unsigned, and it has the range from 0 to 2 to the power of 8, which is 255. Actually, that should be 2 to the power of 8 minus 1, gives you 255. So 2 to the power of 8 is actually 256. But you can't set an unsigned char to 256. Its highest value it can represent is 255. Okay, next we have short, which is short for short int, and this is 2 bytes long. It's a signed integer in the range of -2 to the 15, or -2 to the power of 15, all the way up to 2 to the power of 15 minus 1. So quite large numbers, something in the tens of thousands. Let's have a look. What have I got? The calculator's on some stupid mode. 2 to the 15. It's just shy of 33,000, so a short int can hold about -33,000 all the way up to about 33,000. Okay, an unsigned short is also 2 bytes long. This is a positive integer in the range from 0 to 2 to the power of 16. Once again, I rather stupidly forgot to put a -1 here at the end, but a short int can't actually hold the value 2 to the power of 16. It can only go up to the value 2 to the power of 16 minus 1. Okay, next we've got an int. This is 4 bytes long, and it's a signed value in the range of -2 to the power of 31 all the way up to 2 to the power of 31 minus 1. You'll see lots and lots of these 2 to the power of different things here. Computers absolutely love powers of 2. Yes, because they work in binary, base 2. Next we've got an unsigned int, which is also 4 bytes long, and this is a positive integer from 0 to 2 to the power of 32 minus 1. A long, which is actually short for long int. This is 8 bytes long, and it's a signed integer in the range from -2 to the power of 63 all the way up to 2 to the power of 63 minus 1. Next we've got unsigned to long. So you've basically got signed and unsigned versions of all of these ints. Yeah, 1 byte, 2 bytes, 4 bytes, or 8 bytes, and you can choose signed or unsigned. Anyway, unsigned to long is a positive integer in the range from 0 all the way up to 2 to the power of 64 minus 1. And next we've got the floating point types. So we've got float, which is a 4-byte float, or 4 bytes of memory will be used to store a float variable. And this is a number with a decimal point, e.g. 2.5 or 6.7. So I should have actually put F's here, because floats you should always finish with an F, so 2.5F or 6.7F would be a float. Whereas what I've written here, 2.5 or 6.7, will actually be read by the C++ compiler as a double. Doubles are 8 bytes long, so they're twice the size of a float, and they can hold much, or numbers with much better precision, so much smaller numbers, say 0.000001, or they can hold really large numbers. Yeah, because they're twice as big. Okay, so the final fundamental data type, and there are other fundamental data types, but these are the basic ones. The final one is bool, and this is short for Boolean. George Boole was a fellow back in the 1800s who invented some really clever algebra tricks with a new logic system, and this type is named after him. So bools are basically just true or false. They're similar to a bit. You know, a bit can have 0 or 1, and a bool can can only have true or false, so 2 different values. But instead of using a single bit to store a bool, the C++ compiler will actually use a byte. Anyway, let's move on. So declaring and defining a variable. In C++, a variable must be given a data type, as per the first column of the previous slides. Let's just go back. This column just here. So these are the data types. A name must also be given, and an initial value if you want. Declarations always finish with a semicolon. Yeah, the semicolon is just rampant in all of C++, so yeah, these are statements, they have to finish with a semicolon. And here's some examples. We've got int I and a semicolon. This declares the variable I with no particular value at the start. So that I there could be anything. We're not assigning a value, just whatever happens to be in RAM at the time. At that spot where C++ decides to use I, that will be the value of I. Usually you'd have to declare it or initialize it to some value before you actually use it, but you don't have to. Okay, short b equals 25. This declares a short integer, or just a short, and it sets the initial value, the very first value of b, to 25. Float q equals 4.5f. So here we see another variable. We've called this one q, and the 4.5f just here will be set to that. So q is going to have the value 4.5. Next we've got double d equals 0.9. No f on the end, since this is a double that we're declaring. Bool my bool equals true. That could also be bool my bool equals false, to set up a new boolean variable that's false. And long disparity equals negative 32. That just sets up a long integer. Yeah, so I just wanted to point out that variable names can have more than one letter. Variable names are actually a sequence of letters, digits, and some other characters are also allowed. They're to remind you, the programmer, what a spot in RAM is supposed to be holding. Variable names cannot contain spaces or tabs. They can't begin with a digit either. The first character must be a letter. Some programmers use underscores instead. Actually, I wrote accidentally. There's no space there. Instead of spaces. So I think this is more an old thing. I don't see a lot of this anymore, but it used to be that you'd put underscores instead of spaces. So my amazing variable might be my underscore amazing underscore variable. Okay, that's good. I tend to use Camel Case. A lot of people do nowadays for naming my variables. And this is where the first letter of the name is lowercase, and there's no underscores, but the initial letter of each word after the first one is uppercase. So if I had to name a variable called fuel sum, I might do this, fuel sum with a lowercase f and an uppercase s, or I might do fuel average like this, lowercase f and uppercase a. Yeah, that's called Camel Case. Like commenting, naming variables can make or break a programmer. Yeah, so Visual Studio has a system, it's called Intellisense, where it offers to auto-complete things. So when you start typing, Visual Studio suggests to you what it thinks you want to type next. And this is a massive speed increase. It's a really big help. If you name your variables properly, this Intellisense just here can really help you out. And you don't have to keep checking what you called a particular variable, you know, scrolling up to the top of the screen and checking what you called it and then scrolling back down again to write your expression. Intellisense will just help you out, and you can just type non-stop. Good stuff. If your variables are selected in that, you can, yeah, I'd say you could probably at least double the speed that you program. And actually it's a bit more than this. If you don't name variables properly, then you're just going to get lost and you won't be able to finish a program. Good. Okay, so printing values. Before we get into actually defining and changing variables, it's useful to have a way of printing them to the screen. So here I've just got a little example of how to print a variable to the screen. Int I equals 20, declare some variable, and that equals 20 just there was completely pointless, since on the very next line I've changed it to 33. I equals 29 plus 4, so I will equal 33. We'll look at that in a minute. But this is how you print it out. So cout, or console out, or character out, somebody said in a comment to the last shoot. Character out and then what we're printing is the string, the value of I is, and then colon. And then I use these two insertion operators here to surround the variable's name, I, and then an end line at the end. So this is actually going to print the value of I is 33. Okay, basic operations. So computers are really, really good at math, so they're very, very fast at basic arithmetic. And we can type expressions in pretty much a regular mathematical language to set the values of our variables. And some of the basic operators are the plus, the minus for addition and subtraction. We've got division, which is the slash. I don't know why, but there's never been a division sign on the keyboard, so we use the slash instead. And likewise, there's no multiply sign, so we use the star or the asterisk to multiply two numbers together. And there's also, this one might look a bit weird actually, but the percent sign means modulus. And this gives the remainder after division. It's really, really useful. Yeah. Okay, just a quick note on integer arithmetic. Whenever the variables used in arithmetic are all integers and the answer would normally have decimal places, the decimal places are simply removed. There's no rounding going on whatsoever. So, for example, int I equals 10 divided by 6. Now we know that 10 and 6 are integers here because they've got no decimal point. If we said 10f or 10.0f, then that 10 there would be a floating point value, but it's not in this case. Int I equals 10 divided by 6 is going to set I to 1. Not 2 or 1.6 recurring, it's going to set it to 1. So the 0.666666666 recurring is just going to be chopped off. Int b equals negative 10 over 6 is going to set b to negative 1. Not negative 2 or negative 1.6666666 recurring, it's just going to chop off that 0.6 there and set it to negative 1. And this is called truncation. And this is what integer arithmetic is all about. It seems as though it's just doubling the degree of error each expression that we do, but actually it's really, really useful. Anyway, some examples. Some examples of setting variables. C++ understands the standard rules of operator precedence. So division happens before addition and subtraction, and multiplication happens before addition and subtraction. And brackets are evaluated first. Anything in brackets is evaluated first. So here we've got int j equals 10 plus 7. That's going to set j to 17. We've got int q equals 9 plus j. So you can use previously defined variables in the expression. Now j from the previous line was set to 17, so 9 plus 17 is going to set q to 26. Very cool. Float p equals 1.6f. This sets p to 1.6. Note the f on the end because we're setting a float. Double my dub equals 6.4. Double g dub equals my dub divided by 1. Yeah, all that. No worries. It's just going to set g dub to whatever the answer there happens to be. And after variables are declared, we can reuse them. Yeah, so after you've declared a variable as being a double or a float or an int or whatever, you don't need to put double, float or int at the start. You can just say j equals 9 plus 89. So j just here will be set to 115 since q was 26 and 26 plus 89 is 115. G dub equals my dub minus j. Sets g dub to negative 82.6. Yeah, we'll look into this in more detail later, but just here we've got my dub, which is a double, and j, which is an integer, and C++ is going to temporarily pretend that j is actually a double. Then it's going to perform the minus here, and set the answer into g dub, which is 82.6, or negative 82.6. That's called casting, but we'll look at it later, converting one type to another. Okay, so yeah, whenever you wish to set a float, you should follow the value with an f. Without the f, it means a double. Yeah, it does, really. I think we said that. C++ will actually automatically remove or add the f, depending on whether we're setting a float or a double. So for the float just here, the 65.6 will actually have f added to it. And for the double down here, HJH, really good names, the f just here will be removed, and 2.3 will be converted to a double before it's actually set. Yeah, some compilers might not necessarily do this, so it's a good habit to put the f there if you know you're dealing with floats. Okay, now before we get onto an example, I just want to say this is really, really cool. An impossible leap of faith. So most programmers have probably forgotten just how strange the following is. Variables themselves can be used in mathematical expressions to set themselves. Now this makes absolutely no sense whatsoever, but I'm so used to it now, I think that it makes sense. But basically what I'm saying here is that we can go int p equals 25, then we can say p equals p minus 10. So p equals 25 minus 10, that's going to set p to 15. Mathematically, it just doesn't make any sense, but yeah, you can do it in programming. Bye. Okay, so before we actually say goodbye, we're going to go over to C++ and code a little example. So file, new project, and we'll go empty project. I'll call it tutorial 2. And I'll right click on my solution, add a new item, a C++ file, call it main.cpp. Okay, so last time we did hello world, I thought it'd be cool this time to do something a little more complex, so we'll calculate square roots. Okay, so that's just my basic little program just there. Now what we want to do is set up a couple of double variables. We're going to say double number. Let's say that we want to calculate the square root to 178. Okay, 178 is the number that we're trying to find the square root for. And let's say there's double guess, this is our last guess, equals, I reckon it's probably about, I would say about 11 or so. Our best guess so far. Okay, so basically what we want to say is the guess of that of, oops, program in C Sharp, number is, and then guess. Okay, so right there I'm just printing out these two variables in a little sentence. So it's going to say the guess of the square root of 178 is 11. The error here is around, and then we'll say guess multiplied by guess. Okay, so we're calculating the square root just here, so guess multiplied by guess. If guess is actually the square root, this is going to print 178. If guess is not the square root, it's going to print something else. So, oh no, let's just say here, our guess squared is, good spelling. Our guess squared is guess by guess. And then we'll say this is error by about. And then we'll just take this and subtract it. And all. Okay, so basically we're just printing out three little lines here. The guess of square root is 178. Or the guess of the square root of our number, 178, is 11. And then our guess squared is, and it's going to print out 11 multiplied by 11, which gives 121. And then it's going to calculate how far that 121 is from 178. Good stuff. cin.get. Okay, so this is not actually guessing any square root at all. This is just printing out a bunch of numbers. And if we run that, we should see exactly. Yeah, okay, so we'll just make it a bit bigger. Lucinda. I should probably set these fonts up so that it's always larger in my console windows. Anyway, the guess of the square root of 178 is 11. Our guess squared is 121. This is in error by about 57. So we're pretty far off. Now we're going to use an absolutely amazing, beautiful magic trick, and guess equals 0.5, 0f, 0.5 multiplied by guess plus number divided by guess. Okay, so this trick is from just my best friend, Mr. Isaac Newton. And if guess isn't the square root, which is not in our first example, this is going to bring it closer, exponentially closer. Every time we do this, guess equals 0.5 multiplied by guess plus number over guess is going to give us a better and better approximation of the exact square root of 178. So, if we just copy that and paste it down here, the guess is now going to be closer. And we go cin.get. Remember that cin.get just here is wait for the user to press enter. Maybe we can put up here, please press enter. Something like that. Please press enter. Okay, so let's just run that and see how we went. Okay, so the first time, just our outright guess, which was 11, was in of the real square root by 57 when we squared it. And the next one, there we go. So the next guess, after doing that little trick from Newton, is at 13.5909. So you see it starts to get really accurate really quick. This is in error by about -6. So we've jumped from being 57 units out to -6. That's quite cool. Let's do it again. That's once, twice, 3 times. Okay, so I've just copied and pasted exactly that same thing 3 times. Usually you just do a loop here, but we haven't learned loops, so we'll just copy and paste it. And also usually there is actually a function built into a library, a header, that calculates the square root really quickly, but we're not doing that at the moment. We're just looking at variables. Anyway, if we hit F5, okay, so first run it's 57, next run it's -6.7. Okay, so now we're starting to get really close. Our guess squared, or 13.3439 squared, is 178.061. So that's very, very close to 178 in only 2 moves. This is in by about -0.06. We hit enter again. Bingo. We've almost got it. Our guess squared does equal 178 because there's been a bit of rounding going on. But actually, we're still in by about -5 by 10 to the -6. If we hit enter again, we see that our error is 0. The square root of 178 is exactly 13.3417. It's not actually that exactly. Since 178 isn't a square number, it's going to be an irrational number, the root of it. Anyway, so that's a really good way to guess the square root of things. If this guess here starts out really bad, so maybe we're looking for the square root of that, 1, 4, whatever. I should put 0 here as well. It won't get as close. Like, the closer your initial guess starts out, the better. But this is just a little example of how you can use variables to calculate something useful. And this is just a start, folks. These machines of ours can do absolutely amazing things. Square root's pretty cool, but yeah, that's just a start. Okay, well that's a lot, so thank you for listening. See ya.